Okay, so we are discussing about formation of a decision tree, where at each node of the decision tree we check a condition on an attribute, and then accordingly we take branching to other nodes and until we reach at the leaf node where we have the class level. So we discussed an information theoretic measure by which this attribute is selected, because there are candidate set of attributes at every node when you are forming a decision tree, that one of them will be considered for uh, putting the conditions at that node, that what conditions will be checked based on that attribute. So this is an important important step of decision tree formation, because we would like to keep the tree small in size of the depth. So depth of the tree we'd like to keep as small as possible. Now this information gain is defined based on the entropy of the class distribution uh, at a given point at that node, and if we split that, no, if we can partition those training examples based on the attribute values, um, based on the uniformity of attribute values, and then in the partitioned sets, we also compute the entropies of class distribution. Is there any question? Please mute your microphone in that case. So the average entropy of the partitions induced by the corresponding conditions of the attribute, uh, that is that is computed, and the information gain is the difference between the entropy of the unpartitioned data and the average entropy of the partitioned data with respect to class distribution. Once again, let me highlight that. So the attribute for which this information gain is the maximum, because every attribute will induce different partitions, right? And you will have different information gains for that. So the attribute for which this information gain is maximum, we select that attribute and we form a node and the decision tree at that point based on the corresponding criteria, putting the conditions on that attribute values. So this is the entropy based measure. As you can see here, that at a particular point of the node of the decision tree, we are considering a set of training examples which is under considerations, right? On which you will be inducing the partition based on an attribute A. So consider all possible values of attribute A. We are assuming here that A has only discrete values and it's a finite set. So if I consider all such possible values, so each value will induce a partition in the set S, and for each value, this partition is considered induced to one of the partition, I should say. So for each value, you will have a set S, and then you find out the class distribution of that partition. So if there are n discrete values, there will be n such partitions, or n such partitions. So, and then the weighted average, the weights are proportional to the size of the corresponding partition. So the weighted average will give you, weighted average of this entropy will give you the corresponding entropy of that partitions induced by the attribute A. So the difference between these two is the information gain. That's what I mentioned, and it is a attribute giving the highest gain is selected. So that there would be a reduction in entropy after choosing attribute A, as I mentioned, because you are you are imposing more order in your corresponding data in partitions. An individual partition may have again higher entropy, but overall, if you consider the overall entropy, weighted entropy of those partitions, it has to be less. So the examples already we discussed in the previous class itself, so I'm not repeating them. So this may be one such conditions, and depending upon your set of training examples, this is one set of training examples, and you see that there are two possibilities. So in these training examples, we consider each training example has two attributes only, A1 and A2. And naturally, out of them, here A1 would be selected because the gain is highest. Another example where you have a different kinds of leveling. So it's a different training examples. Though the numbers look similar, but your levels would be different. I mean, it's a different training examples. So there also you have a situation where you can see that in this case, information gain is highest for it. Is high, the information gain is not shown. That is, attributes are shown. Information of the entropy of the particular partition is shown here. So the information gain again it's highest in A1, so A1 is selected. So if we look at certain mathematical properties of this gain function, which is the difference of these two entropies I mentioned. So it's a measure of reduction of uncertainty. So higher the gain value, higher would be the reduction of uncertainty. So the value lies between 0 and 1 in this case. So maximum value is 1 and minimum is 0. And its significance, here you should note also for two classes, the maximum entropy is 1. So significance is that what is meant by gain of 0? It means that you have almost 50-50 class distributions after splitting them. So there is no gain in that sense. What is meant by gain of 1? It means that one of the node would be, at least one of the node would be your pure node, which means you have perfect uncertainty in some nodes. So it is basically finding there. So in this way, with these heuristics, you are trying to keep the depth of the tree small because you are choosing greedily that attribute which will give impose a kind of maximum order of the data at that point. So, excuse me, let me take a 2 minutes break. Okay, so let us continue this discussion. So again, we will be working out with an example, the same discussion just to illustrate it better. So you see here that you have a set of training examples. There are statistics of 14 days. And the last column, it is the outcome that whether you should play tennis or not. And there are 4 attributes of the days which are under consideration. Outlook, which is something like earlier we say the sky condition. It is basically outlook is the environmental conditions. Then the temperature, humidity, and wind speed, or wind in this case, the name of the attribute. And finally, the outcome is that whether you'd be interested to play tennis with this condition or not. So there our task is to provide a attribute of a particular day, and then you are predicting the same. So here in this case, if I if I just look at this particular data, as you see, there are 14 data. So the class distribution in this data, if you look at it, can you tell me what is the class distribution? For example, how many numbers of yes is there and how many numbers of no is there? So if you count it, it's simple counting. Just to tell me what is the class distribution in this case?
So 9, 4.
9 and
5. 5.
9 and 5. Okay. So you have yes 9 and no 5. So what is the entropy of this training data set? That is no, at the root node, you have the whole data set. It is not yet partitioned due to your attribute conditions. So the training example. So what is the entropy? Sorry, this is n and y is 9. I think y is 9, isn't it? Y is 9 and n is 5. So that means there are 14 examples. Yeah. So what should be the entropy? Just you tell me, one of you tell me the computation.
Sir, it's minus 9 by 14 log 2 9 by 14 minus 5 by 14 log 2 5 by 14.
Right. So is there anyone who has not understood this particular computation? If not, please go through the basic definitions of entropy, then you will understand. It is basically finding out the entropy of the whole data set. So what is that value? Did you compute? Anyway, we will be proceeding and we can do that thing. Otherwise, no, please note it.
0.94.
0.9 or something like that. Yeah, so you can see that the result is shown here, 0.94 entropy. Now, our task is to choose the attribute. So what are the candidate attributes here? Candidate attributes here: outlook, temp, humidity, wind. Okay, so these are the set of candidate attributes, and we will be choosing one of them based on the information gain. So here I have shown you the computations if we consider humidity as a candidate attribute here, potential attribute. Now humidity, there are only two values, high or low. If you look at this table, there are also normal. So low is not there. So that was kind of error in my labeling that branch. But there it is having two values, high or normal. Okay. So once again, what is the class distribution of humidity when it is high? What is the class distribution of humidity? So now we are computing the partitions what would be induced by humidity on this set. So every value will have a partition of two sets, isn't it? So what is the number of no and number of yes when humidity is high?
So
can you tell me?
5, 5 no's, 2 yes.
5 no, 2 yes. Okay, so I hope this is correct. I'm not checking. So when the humidity is high, then you have considered yes is 2. That's what you said. Yes is 2 and no is 5. Okay. So yes.
Sir, yes is 3 and no is 4, I think.
Okay. So let me modify.
Yes.
Fine.
Yes.
3 and 4. Right. Total 7 examples are there which has humidity high, and out of them 3 yes and 4 no. So what is the entropy of this partition? How do you define? In the same way as you have said, minus 3 by 7 log of 3 by 7, always base 2 you should consider. Again, minus 4 by 7 log of 4 by 7. Is it clear? Fine. So you get a entropy for this particular computations for this set. Similarly, when the humidity is normal, then what is the class distribution? So when humidity is normal, what is the class distribution? How many yes and how many no?
Sir, yes is 6 and no is 1.
Yes is 6. You see that, which means entropy would be very low, huh? Because you have more ordered data. You can say almost no, you are having almost an uniform node itself. So here also the entropy would be minus 6 by 7 log 6 by 7 and plus 1 by, sorry, minus 1 by 7 log of 1 by 7. So these are the two entropies. Then how do you get the weighted entropy? So you get from there, you get an entropy, and from this class distribution, when humidity is normal, you get another entropy. And then how do you get the, what is the weighted average of these two? Since they have the same number of samples, weight should be 0.5 for each one. So you just simply take the average of these two. That would be fine. But if the samples are different, then weight should be proportional to the sample size. Okay, I hope that is clear. No? In this case, incidentally, it has become that no, the weights are equal. So this is what is the computation. If you look at the computations, you can see that your this entropy of the partition induced. Okay, I will just take a break. Okay, so now as you see, if I take the average of these two, we will get the entropy of the partitions induced by humidity, and the gain would be the difference between these two, or the reduction. So the gain of with respect to humidity is, this is the value. I hope you have understood. So others, I'm just simply just putting those values. For wind also, you will have two partitions because wind has, this attribute has two values, and there you have gain. You can see it is less than the gain obtained by humidity. So humidity would be preferred. Similarly, you have the gain with respect to outlook and gain with respect to temperature. And so which one you should choose? Which attribute you should choose here?
Outlook.
Yeah,
Outlook.
you should choose outlook. Okay.
Outlook.
So in the root node of the decision tree, your condition would be outlook. That means you will be test on the attribute value outlook, attribute outlook, and depending upon the value, you will branch to a certain subtree. So since outlook has three values, you can look at the table, you can see that outlook has three values: sunny, overcast, or rain. So it would induce again three partitions, right? It would induce three partitions for each value. In each partition, you note that the value of outlook is same. So now you look at the conditions of those partitions once again. Now these are the nodes. These are the nodes which needs to be expanded. In particular, you note that when the value is overcast, then there are four training examples in that partitions in that set whatever now we are discussing, and four of them itself is positive, means yes. So in that case, this is a pure node. This is a pure node. If you compute the entropy would be 0. If you look at the entropy, so we should select this node. I mean, we should level this node because it's pure. So level this node of the level of those samples, which is yes here. So you should level it through yes. But the other two intermediate nodes, like nodes created due to the value of outlook is sunny in that partitions, and node for the partition for the rain, value of rain. These are, we can see these are mixed levels. There are mixed levels. So some of them are positive, some of them are negative. So they are impure nodes. And if it is an impure node, again you should go for splitting the node, which means again you should choose a candidate attribute at that point and then choose that attribute which has the maximum gain and then go on doing these things. And you should do it in all the nodes subsequently in the same manner until you reach at the leaf node. Is this point clear? Is there any question? I hope this is clear. So let us consider that here. So another question I would ask you. So what are the candidate attributes at this node? What are the candidate attributes at this node for which you will be looking, you will be considering the splitting? So remember there are 4 attributes of a day. What are they? Outlook, then I think humidity, then temperature and wind. So what are the candidate attributes? Pardon?
Set outlook,
temperature and wind.
No, I'm talking about what are the candidate attributes for which splitting you will be considering. You are saying only
Sir,
outlook.
Sir, every
Temperature.
attribute except outlook.
Except outlook, sir.
Yeah. Why? Why should you do
Because
that?
because in each node they have a particular value of the attribute.
Yeah,
outlook.
because
So-
all these samples, they have the same attribute value. So you won't get any other partition. So it would be with respect to outlook, it would have the same entropy value. So there is no point of going into this because the information gain would be in that case 0, right? Only if because it is discrete values, that's why you are doing it. But no, if it is a continuous value, then no, you have to consider once again. I discussed this thing in the previous class also, but we are discussing only with the discrete value. So let us restrict ourselves to that. So we'll be considering the remaining set of attributes, candidate set of attributes, which are not yet selected at this stage. So basically, at every path, we'll be considering that, right? So which are the remaining set of attributes along that path? Suppose at this point you are choosing, suppose say humidity as your candidate attribute. You are choosing humidity as your attribute for conditions, checking the conditions, and suppose you are choosing the attribute wind for checking the conditions. And after that, the subtree, which will be, you are checking subsequently in that subtree, only 2 attributes are required to be checked, except outlook and humidity, other attributes to be checked. Similarly, in this subtree, except rain and wind, other attributes to be checked. Sorry, not rain, sorry. Except outlook and wind, other attributes are to be checked. Is it clear? So this thing also needs to be tracked. When you are doing it, this thing needs to be tracked, yes. Fine. So here, so you apply the same process, and then you can get the next level of decision tree, the next level of splitting. So just let me use this. See, this is the set is under consideration, and I'm just putting it as the name of the set is sunny. Sunny is the value of outlook, and that is the partitions we will be considering. So out of this set, we will be having 3 attributes, entropy, partitions of induced by 3 attributes and their entropies. So first, what is the entropy of S sunny? How do you compute the entropy of S sunny? Anyone? What is the entropy of S sunny? This set?
Set 2 by minus 2 by 5 dot.
Yeah.
Sir, 2 upon 5 minus 2 upon 5 log 2 upon 5 minus 3 upon 5 log 3 upon 5.
Exactly. You are right. Fine. So that is the entropy. And then you have to consider 3 attributes for their partitions and compute their entropies. So you will, in the same way, you should compute the gain in information gain. And you see that remaining attributes means you have to consider on humidity, then temperature, and then wind. And you can say that no, humidity is giving significant gain. So from the value, it's also we can guess that means humidity is going to create a very near, impure node. Maybe one of them may be a pure node also. So we'll see the result for this data set. But 0.97 is a very high because 1 could be the maximum value of gain. On the other hand, if you choose wind, the value is very low, which means it is almost keeping the class distribution same. 50-50 split.
So,
yeah.
So I just need to confirm that we are choosing the other attributes which are not taken right till now, just because the gain will be 0, right? Information gain will be.
Yeah. I mentioned that. Yes.
Okay, sir. So entropy will be same, and so the gain will be 0, right?
Gain will be 0. So there is no point checking that.
Okay.
Fine. So so which one you will be choosing here? You will be choosing humidity naturally. And if in this way, if we go on splitting, of course, you will find this with this small set of examples, you are quickly coming to the leaf node conditions where every node is pure. And this is a decision tree, what is formed by this particular technique. Is it clear? Okay. So
Yes,
this
sir.
algorithm
Yes, sir.
is there any question?
Sir,
Right. So this algorithm is called,
Sir?
yeah, please tell me.
Sir, we are choosing the best attribute at the highest at the first level, and then we are discarding that attribute. So how is it can be ensured that this is the best possible classification? If otherwise, if we can choose another attribute at first and then the means another sequence of choosing the attributes, so how can we say that the approach that is taken is the best possible approach?
Yeah. So actually, what is meant by best possible classification? What is the measure of your best thing here? What is your measure? See, you are getting a consistent hypothesis itself. So it is doing all the training examples are consistently leveled.
Yes, sir.
Whatever algorithm you apply using this technique, you can always grow a tree where you get a consistent hypothesis. Hypothesis means that is a tree. So how do you measure the that bestness? That that thing. If you compare two such consistent hypotheses, you will be considering one of them is desirable than the others. So what is the measure that you are considering?
Sir, is in every tree the leaf node will be means fully represent the hypothesis space means by
leaf node
using
would be pure. You are saying every tree the leaf node would be pure.
yes, sir, and also there will be.
I told that is guaranteed. That is guaranteed.
Okay. And sir, the minimum depth to get the leaf nodes.
You are saying that your tree should be small. In the sense, depth should be minimum, right?
Yes, sir. Yes.
Right. So naturally, that guarantee is not possible by this algorithm. It's a greedy algorithm. So it's an heuristics we are using. We are trying to get a small tree, but we cannot say that this is the smallest in terms of depth. Okay.
Yes, sir.
So for that, what you need to do? If we want to get the smallest tree, what should you do? What kind of algorithm you should design in that case?
Sir, we can use Gini index.
You can use
Gini index.
I don't understand. Any?
Gini index. Gini index.
Any index means? What is any index? Can you please clarify? Any index you are saying, isn't it? Yeah, I mean, you should respond. I mean, suddenly you muted yourself. What is any index?
Sir, I wrote in the chat box. I'm saying we should use Gini index rather than information gain. I'm not sure.
I mean, randomly you are selecting. You are saying, no? Any index means what? In the chat box, let me see what you have written. Gini, oh, you are saying Gini index, but that don't ensure. See, when you are saying something now, you should think what you are saying. Why Gini index should give you? If I ask you, can you answer?
No, sir.
No, then don't say that. Huh? Just to inform me that you know about Gini index. It's not required. You have to be logical when you are answering.
Sir?
Yeah.
Can we try dynamic programming using different combinations?
So, in what way? Do you have any kind of algorithms? So, what is dynamic programming? You know,
Sir, there will be optimal substructures.
optimal substructure with respect to what?
For the solution.
Hey, you should understand. No, don't just guess and as I mentioned to Manish also. Please think deeply. At least while giving the solutions, give a probable solution. Just don't mention certain jargons and names. That won't help you in understanding the thing. So there you could have told that no, with respect to training examples, still that training examples, I will get the optimal solutions. Incrementally, you will be getting something you should have told. Anyway, so that's not the point. Point is that no, you have to be very precise when you are answering to my questions, because otherwise the time will be wasted. Unless you know properly, don't try to throw your guess in that way. So the very naive way of doing this is that no, you consider all possible topology of decision trees. There is a finite set. You have finite number of conditions, and you can show that there is a finite number of trees. Consider all possible topologies, and then you measure the height for each tree and choose the one which has the smallest tree. That could be one naive solution. In fact, it is combinatorially explosive, you know that, and this problem is NP-hard itself, right? So that's why this greedy method is there. There is no polynomial time solutions for this. So apart from this, so you are trying to keep the tree small. You are saying kind of optimization, optimal definition, optimization criteria that minimize, get a decision tree which is consistent with respect to training examples, but whose depth is small. That is the optimization problem. Apart from that also, if I say from the machine learning objectives, broader perspective, we are actually trying to, it is not, our ultimate goal is not that we should get the smallest tree. Our rather ultimate goal is that we should keep the test error or generalization error small. So your hypothesis should be should have low generalization error. That is your final objective. And for that also, we are assuming that is the kind of inductive bias on the constraint on the trees we are trying to impose, that we are trying to keep the tree height small or low. So this is what actually we are going to discuss. That's why I wanted to take your questions and to discuss and a bit elaborate it. So you see that actually this process can give you a tree in that hypothesis space. So you are not really rejecting any tree, though you are trying to, through your heuristics, trying to derive a small tree, or trying to keep the depth small, but still there is a possibility that you can attain any topology. It is probable in your hypothesis space. It is probable that you can attain any topology. So in that way, like the previous case of concept learning, where we have imposed certain criteria on the form of the Boolean expressions, if you remember that, using particularly those algorithm, candidate eliminations algorithm or find-S algorithm. So there the form of the hypothesis is constrained. So hypothesis space was not complete. But here hypothesis space is complete, which means that your target concept, target function, which is also a decision tree, it is already included because it is complete. And target function is also in the form of a decision tree. So it is included. Now this algorithm, ID3, this algorithm actually what we are discussing so far. So I will present it in a brief bit formal way, with summarizations of the step. So you know that input should be all these training examples, and output would be a decision tree, which is consistent with respect to this training example. So here in the training examples, we have once again attributes and target attributes. As we see that steps, whatever we have worked out, it is just simply, once again describing those steps. So you are creating a root node, and there you are considering the whole training examples as your data set, and then you are of course, it is a check that if your all training examples are having same class, naturally there is no need of creating any tree. That itself is sufficient. You just simply say, okay, whatever your data, it would be the class, and the class level would be there if you assume that there is no error. So it's a trivial case. But naturally, if attribute is empty, return single node with the most frequent level. So that is one of the things that if you find that certain if your attribute space is also not there. So select the best attribute A, and for each possible value vi of A, you are doing it. So it will be basically it's a recursive definition. So you form the subset S of T's whose value of A is vi. So that means you are inducing a partition, and each partition you are computing from with respect to the attribute A, and then naturally if S is empty, then of course you can return by adding a leaf node below with the most frequent level, and else what you do that you can recursively call the ID3 with S with the set of remaining attributes to form the subtree. So which means that once again with respect to this partition, you are basically, when you are saying select the best attribute A, which means there itself we have considered the information gain, and then you are performing the same thing. So what I have highlighted here, as I mentioned earlier also, that in your tree formation process, in a particular path, when you are going to expand a node, you should only choose the remaining set of attributes as your candidate attributes. This is true because you are considering attributes with discrete values only. So this ID3 algorithm is applicable, or in this form it is only applied with the attribute set which has the discrete values. For continuous attributes, you require to modify this algorithm. Particularly these remaining attributes you cannot apply there. So the maximum depth of the tree is the number of attributes in this case, because that is guaranteed. In ID3, at every path you are checking only one attribute. So your depth of the tree is guaranteed by this way. So that is the maximum depth. Right.
Sir.
Yeah.
Sir, in the previous slide, when there was no attribute in the under created root node, the second point. So means how is that case? So there will be no attribute.
Actually, this is a kind of recursive definition. So if you come at an empty attribute set, then no, you have to return. What you should do that return the single node with the most frequency level. Suppose the condition is that if the attribute is empty, then return single node with the most frequency, the most frequent level, which means the attribute does not have attribute values are missing at that point. That is what it is saying. Yeah, this point is we have to get certain conditions when attribute. No, we are considering all attributes are there. If the attribute is empty, return single node with the most frequent level. You understand? This is most likely is not going to occur in most of the situations whatever we are discussing. There may be some exceptional situation. I have to think about that. But so far, you will always get, because at every point you are inducing partitions with remaining attributes, and there would be, and you assume all attributes are valued there. So there should be, there should be some, yeah. But this is trying to take some conditions, yes. So I need to check that part once again, and I can answer you later on. Okay, currently you can ignore that particular comment. Okay, so let us consider what is this hypothesis space search in decision trees. So here, as you can see, that you are conducting a search over the hypothesis space. Like in the previous case also, in the case of concept learning, it was a search over the space of hypothesis there. And in this case, it's a complete hypothesis space, and your goal is to find the best decision tree. Once again, I discussed this part, that how do you say a decision tree is best? Because with respect to consistent consistent hypothesis condition, every hypothesis, if you assume that there is no error in the training set, every hypothesis will fully satisfy the training examples. So you cannot measure with respect to your training error of the, that cannot be a measure here. So the height of the tree could be one possible measure by which you can choose a decision tree which is the best. And I already mentioned that this is an NP-hard problem, and so we are performing a greedy heuristic search without any backtracking. So you are just simply at every point you are expanding the nodes. So these are the characteristics, and we are taking the decisions based on all the data. That means the entropy measures what you are doing. Right. So with respect to ID3 algorithm, once again, the hypothesis space is complete, and its target function means target function is included. We have already mentioned that it's a hill climbing search, and output is single hypothesis. That is another criteria, another conditions, that like FindS method, which is also a greedy method, if you remember, here also you are getting one single hypothesis. It is not giving any kind of version space, etc. Okay? So analogy to breadth-first search, it examines all trees of given depth and chooses the best. So if you consider the breadth-first search, you can see that here the searching of attributes is also something like that. Our splitting of the nodes are following the similar kind of traversal. Whatever the traversal we follow in terms of breadth-first search, the traversal for formation of the tree, creation of the nodes, it also follows a similar order. It has no backtracking, and it is locally optimal from that point, because at every node, when you are optimizing it, it's locally optimal. You are splitting with respect to the maximum information there, and it uses all T's at each step. That is training examples. So all T's in the sense that already the training examples which are considered. So it is only the training examples which are associated with that state. So you should qualify that. And also you can use this algorithm with some modification. You can make it robust to noisy data, which means if you have noisy data, you should not go for a tree which has all pure leaf nodes, which means there is a noise. So any decision you consider with respect to a node, if all are uniform, so the noisy levels are actually making your model more unreliable. So, but you can modify this algorithm in such a way that means you can stop at any point. Say, so if you find your number of training examples at that point of splitting is much less or is small, then you may not go for splitting. What you can do, you can simply consider there are certain measures, certain ways. One way is that you consider the labels of the most frequent labels, what is in that cell, and you just put that thing. Actually, this attribute set is empty. That clause is kind of qualifying these conditions. It is nearly empty in that sense. So if you have that conditions at a particular point where there are number of samples is very less, then you should not go for split. So this is a once again, this is the thing we discussed about in the previous topic, that is the inductive bias. And if you put inductive bias on this case, that is a kind of restrictions on your induction, and that would give you incomplete hypothesis space. And if you give the preference bias, that means you have the complete hypothesis, but you are preferring one hypothesis in comparison to the other. Here the depth of the tree is that preference. So then your hypothesis space may be complete, but you are not searching every point. So that's the incomplete search strategy. So candidate elimination algorithm has restriction bias, where ID3 has preference bias. And in most cases, that means, so these are two extreme cases, but if we consider the machine learning algorithms in general, there are those algorithms have tried to work with both the kind of bias. So it tries to restrict the hypothesis space. Even in that restricted hypothesis space, it imposes certain preferences. It imposes certain preferences of search. So that's why it is saying that it could be a combination of both. So I mentioned that the preference for short trees for in the ID3 algorithm, and the principle which is guiding this particular preference, it's a kind of philosophy in the scientific investigations. I mentioned principle of Occam's razor or principle of parsimony. That means you try to keep your model small. So you will prefer the smaller size model, or complexity should be small. So if you consider the tree size is the complexity of the model, so and if you consider two hypotheses which are satisfying both the training examples in the same way, that means which are consistent, there you should prefer the smaller model. So prefer the shortest hypothesis that fits the data. So justification is that smaller likelihood of a short hypothesis is going to fit your data. Your probability of your fitting is random. Fitting the data is random, it will be less. So you have more order in that case of selecting a model. So there are there are of course other ways to reduce random fits to data. So this is one criteria, but there could be other criteria. So ID3 uses this principle. That means the depth of the tree should be small, but there would be different other way. And how do you compute this complexity of an hypothesis? So that is the challenge. So you are considering depth of the tree, but is it the true measure of complexity? There could be different other ways of measuring it. Say one is that suppose you want to describe a tree. So there are different methods. There are some methods of describing a tree. So you are encoding a tree, and the code length itself could be considered as the size of the tree. So it is irrespective of its depth. We are defining the representation of a tree, the abstract representations, and in terms of computer, say you are representing the tree, that the pointers, etc., by which you can represent a tree, and there is a storage. You have certain kind of storage requirement for representing the tree. Now, if I consider that itself is the size, so we call it minimum description length. So that is the size length of the description of a tree in your linear storage. And if we can consider, representing a tree from that point of view, so that could be another definition. So there could be a variations based on this principle. So we should also look into this problem of overfitting the data. Suppose you go on, if you get a consistent hypothesis, right? If you get a consistent hypothesis, but it happens that your ID3 algorithms, give you that hypothesis, the length is the maximum length. Because in this case, I mentioned the maximum length of or maximum depth of the tree would be the number of attributes. So if there are n number of attributes, maximum depth would be n, and you will find that your tree is also having the depth n. But the question is that whether that would be preferred, whether you should consider that depth. Though you locally you have optimized, locally you are always considering the attribute which is having the more information gain, but maybe at certain points you will find there is more randomness in selecting attributes. So there is no preference in that kind of thing, and there are more randomness. Maybe there is more noise, and those samples or levels are noisy at those stages. I mean, those are cluttering the data at those points. Because your sample set becomes smaller as you go deeper, and the proportion of noisy data, noisy level would be higher in that case, and that would affect your decision-making process. So what is the so this situation is not desirable, and how you in reality what will happen if it happens so that you will find that the generalization error is high. So you have a low training error, but you have higher test error. Now this is a kind of situations when we say this is an overfitting model. So which means there exists another hypothesis which may be of smaller than what we have arrived, and which has higher training error. That's why it was not chosen in that greedy optimization process, but which will have lower generalization error. So that even though it has higher training error, even though it is not consistent, still you will be choosing that because it has low generalization error. So we have to consider that situations, and we should avoid this kind of situation of overfitting. So this is what it is explaining, as I mentioned, that a hypothesis H overfits the training data if there exists another hypothesis H prime such has greater error than H on the training data, but smaller error on the test data than H. So its test data is the reflection of your generalization error. Is it clear? Is there any questions on this? So in that case, you will find this kind of situation that you are having if you use the complexity as a measure of the tree, and for each tree, if we consider that suppose you are increasing the tree depth, and each one is an instance of your tree, at each level is an instance, and if you consider measurement of training and test error at each instance, then you will find that after certain point of the tree growing the tree, after certain point, increasing depth is not really giving you any benefit in terms of generalization error. In fact, you will find that though training error, because it is consistent, it is going to make your hypothesis more and more consistent with the training data set, but actually test error will be increasing, which means your accuracy will be decreasing. As this kind of trend you will observe, and this is a situation at that point. That means this is the size of the tree which may be in the desirable range. After that, actually you are getting data overfitting. So we should try to avoid this kind of situation, and we should try to get our solutions in this range. So with this, let me stop today because the time is over, and we'll start the next class. Let me take the attendance first, and then I will take some questions. Okay. So, any question?
Sir, I had a request. It's regarding our ML quiz number 1. So if the others don't have a problem, sir, could you please shift it to Friday instead of Thursday? Right now it's going to be conducted on 9th September, Thursday.
No,
Because
actually, Thursday is chosen because it is 12 to 1, and so because of that reason, I have kept Thursday. After that, you do not have to rush for any class.
Actually, sir, okay. We were going to have 2 tests that day itself from 2 to 4 in our compilers course. I'm in the BTech batch of computer science.
Yeah, but this will happen. No? This will happen.
Okay.
So let me know from. It is very difficult to decide in this way. You are telling it, but I'm sure that there will be some issues for others also. Is there any kind of has anybody has any? Okay, this suggestion has been taken. I have no issue. Let me tell you first, because it's a regular class. If you want to hold it on Friday also, that is fine. It can be done. Right?
Yes.
Sir,
no,
like on Friday after the ML slot is 8 to 9, right? I have a course that whose slot is 9 to 11, and there is a 1.5 hour test in that slot. So like for me, it is better to have it on the previous day because I'll have a half an hour or 1 hour break.
So you see that we get
Yes,
different opinions. So let us stick to what I have declared.
Yes,
please,
sir.
you have to accommodate it because this will be the situation. We are missing, of course, one regular class also, as you see, and it is only scheduled on the regular class.
Yes, sir, I understand.
Okay, take it with that spirit. And as you understand, this is a relative grading. So your performance will be compared with others' performance also. It looks competitions, but let it be healthy competitions. Okay?
All right, sir. Thank you.
Okay, so with this, let me stop.
Sir, I wrote a question.
Sir, I have one more thing to ask.
Yeah, tell me.
So like it is not regarding what we talked today, but like on the Teams channel, there was a thing that you can put your questions and you'll get a reply or solution for that doubt or something, that question. But like till when can we expect the reply or like the answer of that question?
Usually our TAs will be responding. Okay.
Okay.
So if you don't get any response within say 1 day, then you can again send a reminder. You wait for 1 more day because let them consult and leave a gap of one day, and then you can send a reminder.
Okay. Got it.
Okay. Fine. Okay. Thank you very much. Bye.